If T1 is congruent to T2, then automatically T2 is also congruent to T1. If T1 is congruent to T2 and T2 is congruent to T3, definitely T1 is also congruent to. Therefore, L1, L2 belongs to R and L2, L3 belongs to R implies L1, L3 does not belongs to R. That is 1, 2 is there, 2, 3 is there, but 1 and 3 is not in the set, does not belongs to R. Hello dear students, welcome to this session of mathematics class. I am Mr. Niranjan, the Faculty of Mathematics, Vidhyaashram PU College, the Temple of Excellence. Now in the previous class, we have discussed regarding definition of a relation and types of relation. Now in this session, I am going to discuss regarding the equivalence relation and the problems based on reflexive, symmetric and transitive. So this session is very important session. Definitely you will get one question for 3 marks from these problems. What are the problems today I am going to solve? Definitely you will get one question for 3 marks in your final examination. Now in the last class we have discussed regarding reflexive relation, symmetric relation and transitive relation. So that is a relation or on set A is said to be reflexive if it is A, A belongs to R, reflexive. Symmetric means for all A, B belongs to the set A, B belongs to R implies B, A also belongs to R. That is called symmetric. If for all A, B, C belongs to the set A, then A, B belongs to R and B, C belongs to R implies A, C belongs to R means then it is called a transitive. Reflexive, symmetric and transitive. So if all these three conditions are satisfied, then the relation is called an equivalence relation. Now let us come to the definition of an equivalence relation. Now what is the definition of an equivalence relation? A relation or in a set A is said to be an equivalence relation if R is reflexive, symmetric and transitive. A relation R in a set A is said to be equivalence relation if it is reflexive, symmetric and transitive. Reflexive relation. What is reflexive relation? You know the reflexive relation is A, A belongs to R. Reflexive. What is symmetric relation? A, B belongs to R implies B, A also belongs to R. Reflexive, symmetric. What is transitive relation? A, B belongs to R and B, C belongs to R implies A, C also belongs to R. If these three conditions are satisfied, then the relation R is said to be an equivalence relation. Understood? A relation R on a set A is said to be equivalence relation if it is reflexive, symmetric and transitive. Reflexive, A, A belongs to R. Reflexive, symmetric, if A, B belongs to R implies B, A also belongs to R. Transitive, if A, B belongs to R and B, C belongs to R implies A and C also belongs to R. So if these three conditions are satisfied, then it is called an equivalence relation. Let us take an example. Usually we are going to discuss like parallel lines, set of all lines parallel to, perpendicular to, set of all triangles congruent to, similar to. These type of problems usually we will discuss in this session. Now let us take an example. Usually we are going to discuss problems like set of all triangles in a plane which are congruent to or similar to, or set of all lines which are parallel to or perpendicular to. These type of problems usually will take to discuss for reflexive, symmetric and transitive, that is an equivalence relation. Let us take one problem. Let us take an example. Let T be the set of all triangles in a plane. All triangles in a plane. All the triangles in a plane. Given that, what is the condition? The relation is given by R is equal to T1, T2 such that T1 is congruent to T2. T1 is congruent to T2. That means first triangle is congruent to second triangle. Show that R is an equivalence relation. This is very simple problem, you know. One triangle is congruent to other triangle. So the same triangle, so you can verify the reflexive very easily, symmetric very easily, and transitive also, because let us take first one, reflexive. Let us come to the reflexive. Since every triangle is congruent to itself, you know, you might have been studied. So every triangle is congruent to itself. So any triangle, every triangle are congruent to itself. Therefore, this is a reflexive relation. That means T1 comma T2 belongs to R implies T1 is congruent to T2. That is T1 comma T1 belongs to R implies T1 is congruent to T1. That is A comma A belongs to R. That is A comma A. Every triangle is congruent to itself, that we know. Therefore, it is reflexive. A comma A belongs to R. Reflexive. Next, symmetric. Symmetric means if T1 first triangle is congruent to second triangle, means definitely second triangle is also congruent to first triangle. If T1 is congruent to T2, then automatically T2 is also congruent to T1. That is the second property. That is symmetric. If R is symmetric, because if T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. That is, if T1 is congruent to T2, if first triangle is congruent to the second triangle T2, which implies second triangle T2 is also congruent to T1. T2 is also congruent to T1. Therefore, T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. Therefore, R is symmetric. That is, A comma B belongs to R implies B comma A also belongs to R. T1 comma T2 belongs to R implies T2 comma T1 also belongs to R. If first triangle T1 is congruent to T2, T2 is also congruent to T1. Therefore, R is symmetric. Symmetric relation is satisfied. Now, let us come to the third property. First one is the reflexive, second one is the symmetric, the third property is the transitive. Transitive, let us consider three triangles T1, T2 and T3. If T1 is congruent to T2 and T2 is congruent to T3, definitely T1 is also congruent to T3. That is, first triangle is congruent to second triangle and second triangle is congruent to third triangle, then definitely first and third triangle are also congruent. That is, if R is transitive, since T1 and T2 belongs to R, T2 and T3 belongs to R implies T1 and T3 also belongs to R. That is, if T1 is congruent to T2 and T2 is congruent to T3 implies T1 is also congruent to T3. Therefore, R is a transitive. That is, if A comma B belongs to R, condition, and B comma C belongs to R implies A and C also belongs to R. That is, T1 comma T2 belongs to R and T2 comma T3 belongs to R implies T1 and T3 also belongs to R. This is the condition. That is, so therefore, this is a transitive relation. So hence R is reflexive, symmetric and transitive. Hence it is an equivalence relation. So a relation which satisfies all the three conditions, reflexive, symmetric and transitive, is an equivalence relation. In the examination, they may ask for definition. Define equivalence relation. Give an example. Equivalence relation means a relation R on a set A is said to be equivalence relation if it is reflexive, symmetric and transitive. Reflexive, A comma A belongs to R. Reflexive. Symmetric, A comma B belongs to R implies B comma A belongs to R. And transitive, A comma B belongs to R and B comma C belongs to R implies A and C. A comma C also belongs to R. Now example, for example, set of all triangles such that they are congruent. Set of all triangles which are congruent. So like this. So that is, let T be the set of all triangles in a plane with a relation R defined by R is equal to T1 comma T2. That is, T1 is congruent to T2 is an example for an equivalence relation. Now, this is an equivalence example. Similarly, you can prove set of all triangles and set of all parallel lines. perpendicular lines like that. Let me take one more problem. Let me start with another problem. Now let us consider this problem. Let L be the set of all lines in a plane and the relation is defined by L1 is perpendicular to L2. Here the condition is perpendicularity is given. So there are so many problems like perpendicularity, parallel to. Now let us take one problem, perpendicular to. So let L be the set of all lines in a plane, R be the relation in N defined by R is equal to L1 comma L2 such that L1 is perpendicular to L2. Then show that R is symmetric but neither reflexive nor transitive. Now what is to verify? This is only symmetric but neither reflexive nor transitive. So you know generally one line is not, same line is not perpendicular to the particular line. So therefore it is not reflexive. Straight away you can say R is not reflexive because L1 cannot be perpendicular to itself. The same line cannot be perpendicular to the same line. Maybe it may be parallel. It is not perpendicular. So L1 cannot be perpendicular to L2. So for all L1 and L1 comma L2 does not belongs to R. Since L1 cannot be perpendicular to itself, therefore L1 comma L1 does not belongs to R. That means A comma A does not belongs to R. That means R is not reflexive. R is not a reflexive. This is not reflexive because L1 cannot be perpendicular to, this is the line L1, this cannot be perpendicular to itself. Okay, so therefore this is not a reflexive. Coming to the symmetric property, observe carefully, symmetric. Let us consider two lines L1 and L2. So let us consider the lines L1 and L2. L1 is perpendicular to L2 and L2 is also perpendicular to L1. So if the lines here L1 is perpendicular to L2 and L2 is perpendicular to L1. Therefore, this is a symmetric relation. If L1 is perpendicular to L2, then L2 is also perpendicular to L1. That is, L1 comma L2 belongs to R implies L2 comma L1 also belongs to R. That means L1 is perpendicular to L2 implies L2 is also perpendicular to L1 here. This is two lines. L1 is perpendicular to L2 and L2 is perpendicular to L1. You can say perpendicularity is a symmetric. That is, R is symmetric because L1 is perpendicular to L2 implies L2 is also perpendicular to L1. That is, A comma B belongs to R implies B comma A also belongs to R. Perpendicularity is a symmetric. Now let us come to the third one, transitive. What is transitive relation? R is not transitive because if L1 is perpendicular to L2 and L2 is perpendicular to L3, then L cannot be perpendicular. So this is L1 is perpendicular to L2 and L2 is perpendicular to L3 means then L1 cannot be perpendicular to this L3. So therefore L1 comma L2 belongs to R and L2 comma L3 belongs to R implies L1 comma L3 does not belongs to R. That is, perpendicularity. If we consider the perpendicularity, it is only symmetric but not reflexive and transitive. So in the examination they may ask for two more questions. Give an example for a relation which is symmetric but not reflexive and transitive. Straight away you can give this. This is a example. Perpendicularity on the set of lines is an example for a relation which is symmetric but not reflexive and transitive. Now let us come to the next problem. Let us take this problem. Very simple problem. Thus show that the relation R in the set 1, 2, 3 is given by R is equal to 1, 1, 2, 2, 3, 3, 1, 2 and 2, 3 is reflexive but neither symmetric nor transitive. Now what is given? R is equal to, the relation is given, what it contains, 1, 1, 2, 2, 3, 3, then 1, 2 and 2, 3. These are the elements in the set R in the relation. Now what is to verify? Let us verify. First one is reflexive. Reflexive. What is reflexive? for all A belongs to the set, A comma A belongs to R. A comma A. A comma A belongs to R. See here what is given? 1 comma 1, 2 comma 2, 3 comma 3, all. 1 comma 1 belongs to R, 2 comma 2 belongs to R, and 3 comma 3 belongs to R. What do you say? Therefore, R is reflexive. R is reflexive. 1 comma 1 belongs to R, 2 comma 2 belongs to R, and 3 comma 3 belongs to R. So therefore it is reflective. Okay. Now let us come to the second property. What is the second property? Reflexive. Second one is the symmetric property. Second, symmetric. Symmetric. What is the definition for symmetric? If for all A comma B belongs to the set A comma B belongs to R, implies B comma A also belongs to R. Let us take 1 comma 2. 1 comma 2 belongs to R, right? 1 comma 2 is in the set. Okay. Now 2 comma 1, check whether 2 comma 1 is there or not. So 2 comma 1 is not in the set R. So 2 comma 1 does not belongs to R. 1 comma 2 belongs to R, whereas 2 comma 1 does not belongs to the relation R. So therefore R is not what? Symmetric. R is not symmetric. Oh, followed. R is not symmetric because 1, 2 is in the relation R, but 2, 1 is not there. Now let us come to the third one, reflexive, symmetric, and the third property is the transitive property. Let us come to the third one, transitive. What is transitive? For all A, B and C belongs to the set, A comma B belongs to R and B comma C belongs to R, implies A comma C also belongs to R. Let us take these two elements. Here 1 comma 2 belongs to R and 2 comma 3 also belongs to R. This implies 1 and 3 belongs to R. So 1 comma 3 does not exist. So this does not belongs to R. 1 comma 3 does not belongs to R. 1 and 2 is there. 2 and 3 is there. 1 and 3 is not in the set. Therefore this is not therefore R is not transitive. This is not transitive relation. So the given relation, the given set is, the given relation is only reflexive but not symmetric and transitive. So R is reflexive here but not symmetric and transitive. Okay, hope you are following. So let us come to the next problem. Now let us come to this problem. What is the problem given? Show that the relation R in the set Z, Z is nothing but set of all integers given by R is equal to A comma B such that 2 divides A minus B is an equivalence relation. Equivalence they have given, it is an equivalence relation. That means, so equivalence relation means we have to verify all the three conditions, reflexive, symmetric and transitive. This is very simple problem. So you know Z is nothing but the set of integers. Set of integers means 0, plus or minus 1, plus or minus 2, etc. terms. Right? Set of integers. 0 is included in the set of integer. 0 plus or minus 1 and plus or minus 2. Definitely, what is this? 2 divides A minus B. If you divide by 2, then you are going to get an integer or not. That is to be verified here. So what is the condition? Show that the relation R in the set Z of all integers is given by A comma B such that 2 divides A minus B is an equivalence relation. Now let us take first one, reflexive relation. So R is reflexive because reflexive means what? A comma A belongs to R, B comma B, C comma C. You can choose any integer, any element, 1 comma 1, 2 comma 2, 3 comma 3, 1 minus 1. So 1 minus 1 means here what is the condition given? 2 divides A comma A. That means 2 divides A minus A. That means 2 divides 0. If you take b comma b, 2 divides b minus b. For example, if you take 2 divides 1 comma 1, that means 2 divides 1 minus 1, 2 divides 0. So you can divide 0 by any number. So therefore R is reflexive on Z. That is, R is reflexive because 2 divides A minus A for all A belongs to Z. That is, 2 divides 0. Therefore it is reflexive. If you take 3 comma 3, 4 comma 4, 5 comma 5. So 2 divides 4 comma 4 means that is 4 minus 4 is 0. So 0, you can divide 0. Therefore 2 divides 0. That means the given condition reflexive is satisfied. R is reflexive. Listen, R is reflexive because 2 divides A minus, that is 2 divides A minus A is nothing but 2 divides 0. Therefore A comma A belongs to R. R is a reflexive relation. Let us come to the second, reflexive transitive. What is transitive? A comma B belongs to R implies B comma A belongs to R. Very simple. If 2 divides A minus B, definitely 2 also divides B minus A. That is transitive, reflexive, symmetric, that is symmetric. So R is symmetric if A comma B belongs to R. That is, if 2 divides A minus B, then definitely 2 also divides B minus A. Therefore, A comma B belongs to R implies B comma A also belongs to R. For example, let us consider if 2 comma 4 belongs to R implies 4 comma 2 also belongs to R. That is, if 2 divides 2 minus 4, then 2 also divides 4 minus 4. Okay, that is, A comma B belongs to R implies B comma A belongs to R. That is, if 2 divides A minus B, then definitely 2 also divides B minus A. Therefore, A comma B belongs to R implies B comma A also belongs to R. A comma B belongs to R implies B comma A also belongs to R. Therefore, R is symmetric relation. Then third one, transitive. Come to the transitive. This is also simple. So if once A comma B divides R and B comma C divides R, definitely then A and C also divides R. That is, therefore A comma B belongs to R implies B comma A also belongs to R. R is symmetric. Now let us come to the third property. So easily we can verify the third property. That is, if A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. That means if 2 divides A minus B and 2 divides B minus C, definitely 2 also divides A minus C. That is, 2 divides A minus B and 2 divides B minus C implies 2 also divides A minus C. That is, A minus C can also be written as, add this A minus B plus B minus C, minus this minus B plus B gets cancelled. That's equal to A minus C. So 2 divides A minus C. Therefore, R is a transitive relation. So hence this is a equivalence relation. Hence R is an equivalence relation. It is reflexive, symmetric and transitive. That is an equivalent. So you can divide 0, 2 divides 0, therefore it is reflexive. 2 divides A minus B implies 2 also divides B minus A, therefore it is symmetric. So 2 divides A minus B and 2 divides B minus C, definitely 2 also divides A minus C, therefore it is transitive, reflexive, symmetric and transitive, therefore it is an equivalence relation. Very simple, that's all. Now let us come to the similar type of problem. Now let us come to this problem. What is the problem given? Determine whether the relation, this is very important problem. You may expect this question for the examination for 3 marks. Determine whether the relation R in the set A is equal to 1, 2, 3, etc. up to 14, 13, 14 defined by R is equal to X comma Y such that 3X minus Y is equal to 0 is reflexive, symmetric or transitive. Determine, we have to verify whether it is reflexive, symmetric or transitive. Now what is the condition given? This is the condition given, X comma Y such that 3X minus Y is equal to 0. 3X minus Y is equal to 0 means 3X is equal to Y, Y is equal to 3X. Straight away we will put X comma 3X. That means first element is multiplied by 3 for the second element, that's all. Now, so let us write the elements are 1, 3 into 1 is 3, 1 comma 3. First element is 2, 3 into 2 is 6. Next, first element is 3, 3 into 3 is 9. First element is 4, 4 into 3 is 12. Next 5. 5 3s are 15. 15 is not included in the set. So therefore the elements of R are 1, 3, 2, 6, 3, 9 and 4, 12. Verify. So this condition will be satisfied. 3x minus y is equal to 0. So take first element. 3 into 1 minus 3 is 0. For example, if I consider this 3 into 4 minus 12, that is also equal to 0. So therefore the relation R is equal to 1, 3, 2, 6, 3, 9 and 4, 12. Now let us verify all the properties: reflexive, symmetric and transitive. Let me check. First one, reflexive. What is reflexive? For all A belongs to the set, if this condition is satisfied, A comma A belongs to R. See, 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 1, 2 comma 2, 3 comma 3, etc. 13 comma 13, 14 comma 14 does not belongs to R, not included in the set R in the relation. 1 comma 1, 2 comma 2, 3 comma 3 are not in the relation R. Therefore R is not reflexive. R is not reflexive. R is not reflexive. First verified, R is not reflexive, because by looking this you can say 1, 1, 2, 2, 3, 3 is not there. Therefore it is not reflexive. R is not reflexive. Let us come to the second property, symmetric. What is symmetric? So I will go to the next page. I'll write on this. R is equal to 1, 3, 2, 6, 3, 9 and 4, 12. Now R, second, reflexive, symmetric. Symmetric relation. Verify whether it is symmetric or not. What is the condition? For all A comma B belongs to the R, A comma B belongs to R implies B comma A belongs to R. Verify. Let us take 1 comma 3 belongs to R implies 3 comma 1 does not belongs to R. 1 comma 3 is there but 3 comma 1 is not there. Therefore R is not symmetric. 2, 6 is here but 6, 2 is not there. 3, 9 is there. 9, 3 is not there. And 4 and 12 is included in R, but 12 and 4 is not there. So therefore R is not symmetric. This is not symmetric. So R is not reflexive, R is not symmetric. Come to the third property. The third one is transitive. Transitive property, transitive relation. What is transitive? If A comma B belongs to R and B comma C belongs to R, for all A, B, C belongs to the set, implies A comma C also belongs to R. Verify. Let us take these two elements. 1 comma 3 belongs to R and 3 comma 9 belongs to R, which implies 1 and 3 also belongs to R. Check 1 and 3 is there. 1 and 9 is not there, does not belongs to R. So 1 comma 3 belongs to R and 3 comma 9 belongs to R, whereas 1 comma 9 does not belongs to R. Therefore R is not transitive. R is not transitive. So this is neither reflexive nor symmetric nor transitive, not an equivalence relation. So this is not reflexive, not symmetric, and it is not transitive. So this is an example for a relation which is neither reflexive, symmetric nor transitive. Hope you are following. These are all very simple problems. Just verify reflexive, symmetric and transitive. That's all. Now let us take this problem. Let us come to the problem number 5. Determine whether the relation R in the set of natural number defined by R is equal to x comma y such that y is equal to x plus 5 and x plus y is reflexive, symmetric and transitive. Whether it is reflexive or symmetric or transitive, and it is an equivalence relation or not, that is to be verified. Now what is the conditions given? Y is equal to x plus y and x is less than 4. X is less than 4. X is less than 4 means x is equal to 1, 2 and 3. That's all. The values of x are 1, 2 and 3. What is y? Y is equal to x plus 5. Okay. Now therefore, what is the relation? R is equal to x comma y such that y is equal to x plus 5 and x is less than 4 means x is equal to 1, 2 and 3. That means you can write this as x comma y is nothing but x is equal to 1, 2, 3 and y is x comma y is nothing but x plus 5. So I will write the elements here. R is equal to, when x is 1, y is equal to 1 plus 5 is 6. When x is equal to 1, what is y you are going to get? Y is equal to x plus 5. 1 plus 5, that is 6. When x is equal to 2, y is equal to 2 plus 5, this is 7. When x is equal to 3, y is equal to 3 plus 5, this is 8. The elements are 1 comma 6, 1 comma 7 and 1 comma 8. By looking through the problem, you can say that it is neither reflexive nor symmetric nor transitive. Just you can say straight away, because see 1 comma 1, 2 comma 2, 3 comma 3 is not in the relation, or therefore it is not reflexive. Symmetric, 1 6 is there, 6 1 is not there, 1 7 is there, 7 1 is not there. So you can say it is not symmetric. Come to the transitive, 1 and 6, 1 and 7, 1 and 8. So you cannot consider. So therefore this is neither reflexive, symmetric nor transitive. So you can say that this relation, since this is neither reflexive nor symmetric nor transitive, because I'll go to the next page. R is equal to 1 comma 6, 1 comma 7, 1 comma 8. Now here R is not reflexive. R is not reflexive because A comma A does not belongs to R. That is 1 comma 1, 2 comma 2, 3 comma 3 does not belongs to R. Next, R is not symmetric. R is not symmetric because A comma B belongs to R implies B comma A does not belongs to R. That is, let us take this, 1 comma 6 belongs to R implies 6 comma 1 does not belongs to R. I can take 1 comma 7 belongs to R implies 7 comma 1 does not belongs to R. This is not symmetric. Let us come to the third. R is not transitive. R is not transitive because A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R does not belongs to R. This condition is not satisfied. A comma B and B comma C implies A comma C. This is also not satisfied. Therefore, this is neither reflexive nor symmetric nor transitive. Okay. Now that is regarding this problem. Let us come to the same type problem. Let us consider one more problem. What is the problem? Examine whether the relation R in the set A is equal to 1, 2, 3, 4, 5, 6 defined by R is equal to x comma y such that y is divisible by x. Now is an equivalence relation, that is verify whether it is reflexive, symmetric or transitive. Now very simple. What is the condition given? Y is divisible by x. Y is divisible by x means second term is divisible by first term. Now write down here what is A. A is equal to, write again A is equal to 1, 2, 3, 4, 5 and 6. Now write R is equal to, so since it's a set of all elements in A 1, 2, 3, 4, 5, 6, set of all elements in B, A is also 1, 2, 3, 4, 5, 6. The condition is Y is divisible by X. So 1 will divide 1, 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 5 and 1 6. 1 will divide 2, 3, 4, 5 and 6. That means Y is divisible by X. 3 is divisible by 1, 4 is divisible by 1, 5 is divisible by 1, 6 is a second term is divisible by first term. Next 1, next 2. 2 you can't divide 1, 2 will not divide 1. 2 comma 2, 2 divides 2. 2 will not divide 3. 2 will not divide 3, then it will divide 4. 2 divides 4. Then 2 will not divide 5, 2 divides 6, 2 comma 6. Come to the third, 3 will not divide 1, 3 will not divide 2, 3 divides 3. Then 3 will not divide 4, 5, 3 divides 6. Next, 4, 4 will not divide 1, 2, 3 and 4, 4 divides 4. Similarly, 4 will not divide 5 or 4 will not divide 6. 5 will not divide 1, 2, 3, 4 except 5 comma 5. Similarly, 6 comma 6. These are the elements of relation R. Now check whether it is reflexive, symmetric or transitive. Straight away you can say it is reflexive because first one, reflexive. R is reflexive because 1 comma 1 belongs to R, 2 comma 2, 3 comma 3, 4 comma 4, 5 comma, so A comma A belongs to R. That is 1 comma 1 belongs to R, 2 comma 2 also belongs to R. You can say that R is reflexive. R is reflexive. Let us come to the second property, symmetric. Let us come to the second one, symmetric. Whether R is symmetric or not. Let us check symmetric. What is symmetric? For all A comma B belongs to R, A comma B belongs to R implies B comma A also belongs to R. Now, what is, let us take this element 1 comma 2, 1 comma 3. 1 comma 3 belongs to R implies 3 comma 1 does not belongs to R. 1 divides 3, but 3 will not divide 1, right? Similarly, you can take 2 comma 6. 2 comma 6 belongs to R, but 6 comma 2 does not belongs to R. What do you say? Therefore, R is not symmetric. R is not symmetric. R is reflexive but not symmetric. Let us verify the transitive property. What is transitive property? A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. Let us consider the transitive. Let us take, I will take this 1 comma 3 belongs to R and 3 comma 6 belongs to R implies 1 comma 6 does not belongs to R. Okay. 1 comma 3 belongs to R and 3 comma 6 belongs to R implies 1 comma 6 belongs to R. Similarly, I can take 2 comma 4, 2 comma 2 belongs to R and 2 comma 4 belongs to R implies 2 comma 4 also belongs to R. So you can say that R is transitive. Let us take 1 comma 3 and 3 comma 6. 1 comma 3 belongs to R and 3 comma 6 belongs to R implies 1 and 6 also belongs to R. Then I will go to the next page. So no space. Let me solve here. Reflexive, symmetric and transitive. Third property is transitive. Transitive. That is, what is the property? A comma B belongs to R. A comma B belongs to R and B comma C belongs to R implies A comma C also belongs to R. Let us take this element. 1 comma 3 belongs to R and 3 comma 6 belongs to R implies 3 gets cancelled, 1 comma 6 belongs to R. 1 and 6 is also in the set. Suppose if I take 1, 2 and 2, 4, so you will get. So therefore R is, what is R? Transitive. So here R is reflexive but not symmetric and it is transitive. This is an example for a relation which is reflexive and transitive but not symmetric. Now, let's come to the next problem. Show that the relation R in the set of real numbers is defined by A comma B such that A is less than or equal to B is not neither. This is reflexive nor symmetric nor transitive. Reflexive nor symmetric but transitive. It is transitive. Now, this correct it. Now, let us verify. Let us verify whether it is reflexive, symmetric and transitive. What are the conditions satisfied? Now, let us take R is equal to A comma B such that A is less than or equal to B. So, clearly R is reflexive because A comma A belongs to R implies A is equal to A comma A, B comma B. B comma B belongs to R means B is equal to B. So, the given condition is satisfied. Less than or equal to, it should be less than or equal to A comma A is equal to A, B is equal to B, 1 is equal to 1, 2 is equal to 2. So, therefore, R is reflexive. Now let us come to the symmetric. This is not symmetric because if A is less than B implies definitely B is not less than A. B is greater than A. So A is less than B implies B is greater than A, not less than A. So therefore this is not a symmetric. That is, if 2 is less than 4 implies 4 is not less than 2. 4 is greater than 2. Therefore this is not symmetric. So 4 is greater than 2. It is not a symmetric. Let us come to the transitive. Transitive, if A is less than B and B, yes, B is less than C, definitely A is less than or equal to C. That is, if A comma B belongs to R and B comma C belongs to R, A comma C also belongs to R. That is, if A is less than or equal to B and B is less than or equal to C implies A is less than or equal to C. So therefore R is reflexive and transitive, not symmetric. This is reflexive and transitive but not symmetric. Okay, let us meet in the next class. Thank you very much.